Hello everyone, my name is Chung-Yeon Lee. Today I'm going to be talking about our work on visual perception framework for an intelligent mobile robot. Recent development in robotics and AI have advanced the technologies into navigation manipulation and vision analysis such as object detection and face recognition. The robot's image recognition accuracy and manipulation precision have already surpassed human beings. What is needed for the robot to be grown is knowing what to look for and how to manipulate by itself. And for this, physical and semantic understanding of the dynamic environment in which the robot is operated must be preceded. Various sensors can be used for environmental understanding, but visual perception will be dominant. Our goal is to develop the system that produce abundant 3D and symbolic level representations of observed people and environment using camera sensors to perform tasks in complex real-world environments. So what should the robot perceive? First of all, object. We divided the object detection process into two levels in consideration of the semantic hierarchy. For example, in this picture, we can tell these objects bottles or beverages, or they could be called as their product name Aquarius and Pocari Sweat. How does the object recognizer to be mounted on the robot recognize them indifferent? The simple method we took is to label objects with coarse and fine-grained labels. First, the primary detector trained with coarse labels extracts the target objects from the entire image, and then secondary detector trained with fine-grained task-relevant labels detects specific class of object. Since the primary detector is designed to operate at all times, we adopted YOLO V3, a model that shows high accuracy with low memory usage and high processing speed. The secondary detector learns the objects as fine-grained labels, taking into account each task the robot needs to perform, and it is only used when performing that task. We have simply divided it into two detectors, but depending on the problem, the semantic hierarchy can also be divided into multiple levels. Human is another important target the robot needs to recognize. What we want to focus on here is what part of a person is used to know who this person is. Face recognition is generally used for person identification. The problem, however, is that the robot is not always facing the human face, and it is not easy to collect the large number of data required to train the general recognition model. Therefore, we propose to use the person re-identification method, which has been actively studied in the field of surveillance systems. In particular, we use verification rather than recognition based on the person re-identification method. This method compares a small number of images taken when a person is remembered with a new input image of the person to determine whether they are the same person based on the similarity derived from deep neural networks trained by images of numerous arbitrary people. This visual learning method is vulnerable to changes in human direction, lighting, and background. Therefore, we made the robot continue to acquire images of people recognized on the move and build up the reference image group. Our pose estimation module uses open pose model to detect joints of a person and to infer the association scores between the detected joints. To solve the instance matching problem between the object detector and pose estimator, we only use the cropped images of people detected by the object detector module as an input to this method. We resize each cropped image to 92 by 164 pixels and build a mini batch of all cropped images to process the pictures of all detected people in parallel. Since individual people are already cropped, we could omit the bipartite matching for assigning joints to each individual and naturally got faster execution speeds compared to other methods for multi-person human pose estimation. All of the things described so far were perceptions of a single object, but in order to understand the situation by watching the whole scene, it is necessary to recognize the relevance of multiple objects included in the scene. Scene captioning is one of the ways to deal with this problem. Based on the attention mechanism, it generates sentence candidates that describe the image. We use this method to find out at a glance the rich information that is difficult to extract with individual objects alone. For example, a situation in which a woman wearing a black shirt is sitting on a couch can be described by a single or combination of two captions. We also use the multimodal data extracted from scene images to improve the relocalization performance of Visual SLAM by augmenting the geometric features. We implemented our visual perception framework on top of the robot operating system ROS to connect and control the robot platform with useful software libraries and tools. To reach high usability, our framework is written in Python language, and we used the TensorFlow and PyTorch libraries as the backend for deep neural network models. The picture on the right side shows the entire modules of our robot API, and the red colored boxes are the modules for visual perception. To carry out the service robot scenarios with the proposed method, we used two famous robots, Pepper from SoftBank Robotics and Human Support Robot from Toyota, also called HSR. We first developed and tested our method in a model house of our lab. In the house, we conducted diverse scenarios such as the person following and guidance, tidy up the house, and food delivery task. This is a snapshot of the food delivery task. In this task, the robot recognizes and counts drinks ordered by people among all bottles on the dining table. Our Pepper robot moved to the kitchen, found and approached the dining table. Then it detected all bottles and cans and successfully recognized two cooks by using the object detectors. To evaluate the person identification module, we set up the follow-up task and the recognition task with various conditions. In the follow-up task as shown in pictures of A, the robot required to remember a person named Mike and follow him. To make confuse the robot, the operator moved through a corner and anonymous people are intervened. As a result of 10 follow-up experiments, all of the person identification was successful. An intercepted person was misidentified as the target person only once. In the recognition task as shown in picture of B, the robot required to identify 3 people while they are moved out of and returned back to the living room. Among 10 trials, the robot recognized the 3 people correctly 8 times and missed 1 person for the other 2 trials. Our robots competed in international robotic challenges, and the visual perception framework was successfully used to solve various tasks in home and restaurant scenarios at the RoboCup 2018 and the Partner Robot Challenge at the World Robot Summit in same year. Here I briefly introduce some tasks carried out in the robotic competitions. First, the restaurant scenario of RoboCup at home. Our Pepper robot performed this scenario in Tim Hortons Cafe in Montreal Convention Center. Our navigation system helped the robot to move safely and accurately between customers and the bar, despite the narrow aisle and densely grouped tables. The robot also correctly detected tables and hand-waving customers. The object recognition module was essentially used to notice the ordered items at the bar. Additionally, person identification modules allowed the robot to remember both the barman and the ordered customer, allowing the robot to complete the food delivery task successfully. Next, the Bring Me scenario of World Robot Challenge. In this task, the robot was asked to get an object specified by an operator, come back and find the operator moved to another place, and finally deliver the object to the operator. Object detection and semantic mapping with respect to the observed objects were necessary to search for all items in the house. Person identifier assisted the robot in remembering the operator and finding him later. To summarize, we effectively integrated various visual perception methods for service robots, such as multi-level object recognizer, reliable person identification from crowd based on whole body images, human pose estimation and gesture recognition, scene captioning, and object-aware Visual SLAM system. Then, we implemented our framework to be ROS compatible. Finally, we validated capability and performance of the implemented framework through many challenging tasks at international robotics competition using 2 mobile robots. Thank you for hearing my presentation, and if you have any question, please don't hesitate to send an email to me.